This is question 13 from the second CSAT sample paper. Here we're told we have K triangles which are all right angled and all have this angle 360 over K, and this angle is A, the right angle is at B, the other point is C. We're told that K is greater than or equal to 5 because otherwise we'd have A being a right angle, which doesn't work. We're told AB at the start is 1, and the way the triangles are related is, we can see these triangles are going to be similar because we've all got a right angle on, and this angle is the same, so this angle is going to be the same, so they're all going to be similar. And we start with this triangle, with AB being equal to 1, and in the next triangle we place so that the equivalent side, the side joining alpha to the right angle, is on the length AC of the previous triangle, and then we keep adding them in this way. So we're making a spiral, and in fact because there's K of them and the angle's 360 over K, actually the last triangle will end up touching here, so we'll get a full spiral. It will come out here somewhere and we'll have a last triangle, something like that. So what we're asked to do is to find the area of all K triangles. So if you want to have a go at this question yourself, pause the video now. Okay, so how are we going to approach this? Well, we said the triangles are similar, so that means if I can find the ratio between the lengths of one to the lengths of the next, then that means I can find the ratio of their areas, and hopefully I can add those all up. So what it looks like I want to do is, because I know this length here is 1, if I find the length of this side, then the ratio of this length, AC, to 1 will give me the ratio between the lengths of the triangles. So let's just try to find AC. Well, that's not too difficult because we have a length and we have an angle, and it's a right angle triangle, so we can just use the definitions of the trig functions. So cos of alpha is adjacent over hypotenuse, which is 1 over the length AC, and therefore AC is going to be sec alpha. So that tells me this length here is sec alpha, so the ratio of the lengths of the second triangle to the first is sec alpha. So what's the ratio of the areas? The ratio is going to be sec squared, because each of the lengths is going to increase by sec. So we can say the area of the second triangle is going to be sec squared, the next one is going to be sec to the 4. So the area of the nth triangle is going to be sec squared to the n minus 1, because we've multiplied by sec squared n minus 1 times. Times the area of ABC. So once we know the area of this first triangle, then we can multiply them all by sec squared, and we have a geometric series which we can add up. So let's try and work out the area of triangle ABC. Well, the area we can just do half base times height. So the height is going to be tan of alpha, so we can do it that way. And then this horizontal is 1, so we do half times tan. We can also do it with the half AB sine C, so because we already worked out this is sec, so we get sec times 1 times a half, and then sine of alpha, and sine times sec is tan again. So again, either way we get a half tan alpha. And that means, what's the area of the K triangles? Well, we have a half tan alpha for the first one, and then for the first we've got 1, and then we multiply by sec squared each time, so 1 plus sec squared etc. all the way up to sec to the 2 times K minus 1. And what does this come to? Well, it's a geometric series, so we just use the formula. We've got sec to the 2k alpha minus 1. So bear in mind the common ratio here is sec squared. So we get sec to the, it's like sec squared to the k plus 1 here, so we go up to sec squared to the k, which is sec to the 2k minus 1. Bear in mind sec's bigger than 1, so we write it this way around, so it's not negative. And we've got sec squared alpha minus 1 on the bottom. So the only thing now we can do to tidy this up is to notice that sec squared is 1 plus tan squared, or sec squared minus 1 is equal to tan squared. So we've got tan squared on the bottom, tan here, and they're both positive, so we can just divide, we can cancel tans. So we get sec to the 2k alpha minus 1 on top, and then 2 tan alpha on the bottom. You might try to factorise this, but it doesn't seem to factorise. I can't get a computer to simplify. You can't simplify it, I can't get a computer to simplify it. So it looks like this doesn't have a nicer form than this one. What you could do is multiply top and bottom by cos to the 2k and get 1 minus cos to the 2k on top and 2 sine cos to the 2k minus 1 on the bottom, which is nice if you prefer sines and coses, but it's not really simpler than this. So this is going to be our final answer. If you want to set yourself a special challenge, you might try to work out what the limit of this is as k goes to infinity. That might be an interesting thing for you to try to calculate.